let's go ahead and start here. So what if I had, let's write some things down. Co-21A. Today is the 23rd. Let's say we have the following. The limit is x approaches 0 of 1 minus cosine of x all over sine of x. Like with any limit, the first thing we should try to do is plug in what x is approaching. So when I plug in 0, I end up getting 1 minus cosine of 0 all over sine of 0, which is 1 minus 1 over 0, which is 0 over 0. Which means we have to do something. Here, like with things with square roots, I would multiply by a conjugate. And now there's a reason for this, specifically because if you multiply 1 minus cosine or 1 minus sine by its conjugate, something special happens. If you multiply by 1 plus cosine over 1 plus cosine, like with any conjugate, you want to multiply out the parts that are conjugates and leave alone the parts that are not conjugates. So I'm going to leave the bottom alone. I'm just going to leave it as sine of x times the quantity 1 plus cosine of x. And the numerator, 1 minus cosine of x times 1 plus cosine of x becomes 1 squared minus cosine squared, or just 1 minus cosine squared of x. The reason that's notable is because there's a trig identity that we can use, which is that sine squared of x plus cosine squared of x is equal to 1. Or if I subtract cosine squared from both sides, sine squared of x is equal to 1 minus cosine squared of x. So I can replace 1 minus cosine squared of x with sine squared of x. So I've got sine squared of x on top now. On the bottom, I still have sine of x times 1 plus cosine of x. But now, sine squared x divided by sine of x, I can divide out one of those signs. And I'm left with just the limit as x approaches 0 of sine of x over 1 plus cosine of x. And then I've dealt with the problematic part. Now, if I plug in 0, I don't get 0 in the denominator. I get sine of 0 on top over 1 plus cosine of 0 in the denominator, which is 0 divided by 1 plus 1, and 0 divided by 2 is just 0. So this limit ends up being 0. Let's look at some more trig stuff. What about the following thing? The limit as x approaches infinity of sine of x divided by x. So here, you can't really, so sometimes you can kind of plug in infinity and think about what's happening. Sine of infinity is not something that really makes a lot of sense. Because when I think about the sine graph, I think about this function that keeps oscillating back and forth, back and forth, back and forth, back and forth, and it doesn't ever get close to any one value. So I can't really think about this doing anything other than say, well, I don't know. This is a prime example of when we want to appeal to the squeeze theorem or the sandwich theorem. And it's generally true. When you have sine or cosine and the insides are getting infinitely large, going to infinity, it's usually a good time to use the squeeze theorem. So if I'm using the squeeze theorem and I'm involving sine or cosine, I'm usually starting with the fact that sine or cosine, in this case sine, of whatever is between -1 and 1. That is always true. No matter what you're taking sine of, it's always bigger than or equal to -1. It's always less than or equal to +1. And then the usual kind of idea is that we're going to try and make the middle part look like the thing we're trying to take the limit of. So in this case, I'm going to divide everything by x. So I have -1 over x less than or equal to sine of x over x less than or equal to 1 over x. Sometimes with the inequalities, you have to be worried about, like, did I multiply both sides by a negative thing? In this case, that's not an issue because we know x is positive because x is going to positive infinity. So I divided everything by x, but x is positive, so it doesn't change the direction of the inequality. Really, it's usually not something you actually have to worry about, but it's good to be aware of. All right, so now I've got the thing I want to take the limit of in the middle, so I don't take the limit of it. Take the limit of the outer parts. The limit as x goes to infinity of 1 over x. Here's something that we will say a lot, that I will say a lot. If the denominator gets large, the fraction gets small. And if the denominator gets small, the fraction gets large. Sometimes positively large, sometimes negatively large, depending on if the overall fraction is positive or negative. But that's the idea. So here, since the denominator is getting really, really large, the entire fraction is getting closer and closer to 0. So the limit is 0. And similarly, the limit as x goes to infinity of negative 1 over x is also 0. And since the limit of this is 0 and the limit of that's 0, by the squeeze theorem, the middle part has to get closer and closer to 0. There is no other choice. So we can say by the squeeze theorem or the sandwich theorem, whatever you like to call it, the limit as x goes to infinity of sine of x divided by x is equal to 0. Which one? Negative 1 over x? For the same reason that the first one is. If so, the denominator is still getting very, 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 very big, which means the overall fraction is getting very, very small. It's getting small. It's a like, for example, if x is 1,000, 1 over x is 1 over 1,000. If x is 1,000,000,000, 1 over x is 1 over 1,000,000,000. It doesn't matter if it's positive or negative, it's still really, really close to 0. Yeah.
Are they like technically not equally 0, like 1 over x?
Right. So here's some important notation stuff. A good question. Glad you asked that. So it is true that f of x equal to 1 over x never is equal to 0. So what do we mean when we say that, I should say, but it is still true that the limit as x approaches infinity of 1 over x is equal to 0. And I use those words explicitly and purposefully. So this notation doesn't mean that the function ever equals 0. What this means is that as x gets larger and larger, f of x equal to 1 over x gets as close to 0 as we want. So all this expression here means is that the function 1 over x gets really, really, really close to 0. But instead of saying all those words every time, we're going to use the shorthand notation to say, oh yeah, we're going to say the limit as x goes to infinity of 1 over x is equal to 0. And we're all going to agree that we know that that means that the function just gets really close to 0. So yeah, this doesn't mean the function ever equals 0. It just means it gets really, really, really close to it. You really wanted to, it's not great. I don't love that. I don't really want to. Not that I want to, I don't want to hear. I would also point out that in a similar way, similarly, we could say that the limit as x approaches 2 of x squared plus x minus 6 over x minus 2 is equal to 5. Let's show the work. Limit as x approaches 2. If I actually plug in 2, I get 4 plus 2 minus 6, which is 0, over 2 minus 2, which is 0. And we know 0 minus 0 is a problem. So we'd factor out the numerator factors. So let me ask you all. when I plug in 2 and I get 0 on top, I know then that what has to be a factor on top. Right. And if I know x minus 2 is a factor, I can determine really easily that the other factor had better be x plus 3. Because x times x has to give me x squared, and 3 times -2 has to give me 6. Then, and I want to remind you, if x is approaching 2, that means x is getting really, really close to 2, but not equal to 2. X never gets to be 2. It's getting really, 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 really close to 2. Like 2 point, all the zeros you want, 1. I don't want to say all the zeros, right? Okay. So what that means is, whatever x is, it's not 2. And so x minus 2 is not 0. And x minus 2 divided by x minus 2 is the not 0 number divided by the same not 0 number, which has got to be 1. I'm taking a long path to say here that x minus 2 divided by x minus 2 is 1, or they're going to cancel. But I don't love using that word. This is equal, the limit is x approaches 2 of x plus 3. And again, all we're asking with this question is, what is x plus 3 getting really close to as x gets closer to the number 2? Oh, well, if x is really close to 2, then x plus 3 is really close to 2 plus 3, which is 5. And we do, in fact, say that the limit is equal to 5. The function never equals 5. In fact, I'll graph the function if you want to see it. I'll graph it right here, even though it's kind of terrible to graph it here. This function looks like the straight line, y equals x plus 3, except there's a hole at the point when x equals 2 and y equals 5. The hole right there, and the graph looks kind of like this. Hole at the point 2, 5. And so we can see that x can get really, really, really close to 2, and the y values can get really, really, really close to 5. But again, instead of writing all those really, really's and close to's, we just say the limit as x approaches 2 of this function is equal to 5. And that has all that meaning for us. Yeah. Uh-huh. So one more time.
When should you know that they're gonna say what's?
That's a good question. That the answer really is with experience. But a more specific answer is, I typically know I should try to use the squeeze theorem or the sandwich theorem when I see a limit where I have a sine or a cosine and the inside of the sine or the cosine is getting infinitely large. Let me give you another example. Let's say I wanted to find, sure, maybe if I can move these pages there. The limit as x goes to infinity of 4 cosine of x plus 3x squared over 2x squared plus 1. So there's a couple different ways to approach this. I personally prefer to try to just use the squeeze theorem largely, although I'll mention another way of approaching this as well. So here's what I would start with. I say, okay, well, I've got cosine of something, and the inside something is getting infinitely large. So I know that that's a good shot that I might want to use the squeeze theorem. Or I usually say squeeze. You can say sandwich, right? I'm just going to say squeeze. You know, I mean squeeze or sandwich. I feel like there's another way of saying it too, but whatever. So I'm going to start with cosine of x between -1 and 1. And I'm going to try and make the middle of this compound inequality look like the thing I'm trying to take the limit of. So first I'm going to multiply everything by 4. So I have -4 less than or equal to 4 times cosine of x less than or equal to 4 times 1. And then I'm going to add 3x squared to each side. I'm going to have 3x squared minus 4 less than or equal to 3x squared plus 4 times cosine less than or equal to 3x squared plus 4. And then I probably wouldn't actually write another line. I'd probably just divide each thing by denominator. But if I can write one more line, say, oh, now I'm gonna have 3x squared minus 4 divided by 2x squared plus 1 less than or equal to 3x squared plus 4 cosine of x divided by 2x squared plus 1 less than or equal to 3x squared plus 4 divided by 2x squared plus 1. And then we can take the limit of the outer parts. So what's the limit as x goes to infinity of 3x squared minus 4 over 2x squared plus 1? Well, the longer way, so there is a shortcut for this, but I want to show you the longer way. So the longer way is either to divide everything by the highest power of x that's in the denominator, or I'll do it that way first, and then I'll show you the other way of doing this, the second part. So if I divide everything by x squared, look what happens. I get 3x squared divided by x squared minus 4 divided by x squared over 2x squared divided by x squared plus 1 divided by x squared. Technically, I've really multiplied the top and bottom by 1 over x squared, which is really just multiplying by 1, so I haven't changed anything. And then I'm going to simplify a little bit. I'm going to write this as the limit as x goes to infinity of 3x squared divided by x squared is 3 minus 4 over x squared over 2x squared divided by x squared is 2 plus 1 over x squared. Now, as x gets really, really big, what happens to 4 divided by x squared? Really big or really small? Really small. How about 1 divided by x squared? Also small. So I end up with 3 minus 0 over 2 plus 0, which is just 3/2. But I have to check the other side. So now I'm going to do the limit as x goes to infinity of 3x squared plus 4 divided by 2x squared plus 1. Now, if you look at the work I just did, you could probably see that if I change that minus sign to a plus, my answer is still going to be the same value of positive 3/2. I do want to show you, though, a slightly different way that people like to write this, just because some people prefer to divide everything by x squared. Some people prefer to factor out the highest power of x in the denominator. Doing it that way, if I factor out an x squared from the numerator and the denominator, well, in the numerator, I'm going to have x squared times the quantity 3 plus 4 over x squared. In the denominator, I'm going to have the x squared times the quantity 2 plus 1 over x squared. And then those x squareds get to divide out to 1. X squared divided by x squared is just 1. So you really are left with the same way, it's just a slightly different way of getting there. And then the limit as x goes to infinity of 3 plus 4 over x squared, well, the 4 over x squared is getting really, really small. And the 1 over x squared is getting really, really small. So I get 3 plus 0 over 2 plus 0, which is 3/2. And then since the limit of this is 3/2, and the limit of that is 3/2, by the squeeze theorem, the middle part has to have a limit of 3/2 as well. So by squeeze theorem, the limit as x goes to infinity of 4 cosine of x plus 3x squared over 2x squared plus 1 must be 3/2. All right. Continuing with trig stuff, but switching gears a little bit. We talked just now about the limit as x goes to infinity of sine x over x and end up being 0. We're going to look at that same expression, except we're going to change what x is approaching. So we're going to look now at the limit as x goes to 0 of sine of x over x. You might know what this limit is already. You might have learned L'Hopital's rule in the past. But I really, really, really would like actually to show all of you why this limit is equal to what it's equal to. I probably would not encourage you to write all of this down, although you're always welcome to. I don't think you need to be able to reproduce this geometric proof I'm about to show you. Has any of your teachers done have any of you seen the thing I'm about to show you, but you haven't seen yet? Dumb question, right? Has anyone talked about the geometric proof of this? The limit is x goes to 0 of sine x over x. Okay. I do think it has value. I don't think you'll ever have to reproduce it, but I do think it's good to see so you can maybe just a little bit more believe that this limit actually is equal to 1. I will give some graphical proof just for a second here, so everyone can look at Desmos for a minute. So I think it's always nice to look at Desmos and see what things look like. Should have had this ready to go. Sorry. Not prepared. But if we graph y equal to sine of, why am I using capitals? That's terrible. Y equal to sine of x divided by x. We zoom in a bit. So you can see, oh yeah, look, I mean, the y value, the x values are getting close to 0. The y values are like 0.92, 0.93, 0.94, 0.95. And we get really, really, really close to 1, but actually at the point there, right? It's so close to 1. Desmos is telling me it's 1 because it can't approximate any better. But if you actually get over there, it's undefined, right? Because if you plug in 0, you get 0 over 0, which is undefined. But you can see both from the left and the right, the y values certainly seem like they look like they're very, very, very close to 1 as x is closer and closer to 0. Cool. Okay, here's some geometry that I think is so I think this proof is really neat. I will try to do it as quickly as possible to not take too much time. But here's the idea. We're going to look at a circle of radius 1. Actually, not even the whole circle. We're going to look at a slice of pi from this circle. So this circle, the radius is equal to 1. I'm going to label some points here. So let's call the center of the circle O, like for the origin. We'll call this point over here A. And I'll point out the length of OA is equal to 1. I'm going to draw another point on the circle. Let's call that point on the circle B. I will also point out that the length of OB is 1. And then I usually like to use theta instead of x. Doesn't really matter what you use, but let's use theta. Let's call this angle theta. That's usually the standard choice for an angle name if you've got to pick something. And then we're going to do 2 more things. We're going to drop a perpendicular from B onto the segment OA. Let's call that point there C. It's a right angle. And finally, we're also going to draw the arc from C to the segment OB so that this length here, let's call that point P, the length OP is the same as the length OC. Questions so far? And in general, feel free to stop me and ask questions at any moment. Just say words or write something in the chat. Okay, so here's what I want you to see. This slice of pi, OCP, is smaller than this triangle, OCB, is smaller than this larger slice of pi, OAB. So I'm going to say the sector, I'm going to try and draw it curvy here. That's a sector. Sector OCP has less area or less than or equal to the area of the triangle OCB, and that has less or equal to the area of the larger slice of pi or the larger sector OAB. Try to make my sectors look like pieces of pie. Try to make my triangles look like triangles. Okay, now we're going to find some formulas for these things. So, does anyone know the formula for the area of a sector? Why would you, right? Like, why would anyone really? So, I'll remind you all, to the side here, that the area of a circle is pi times the radius squared. Or as I would write, and I'm going to write, not as I wouldn't usually write, but here I'm going to write that that's equal to 1/2 2 pi times r squared. there's not a really good reason for this other than it's going to show you what I want you to see. What about the area for half a circle? Well, that would be half of this. So it'd be half of pi r squared. So the area for half of a circle is 1/2 pi r squared. Here's what I want to point out. In radians, what's the angle measure for one full circle? That's in degrees, which is correct. But what is in radians? 2 pi. How about the angle for half a circle? Pi. Well, look, the area of the whole circle is 1/2 times the angle for the whole circle times r squared. The area for half a circle is 1/2 times the angle for the half of the circle, pi, times r squared. And this formula is generalizable for any angle. So the area of a sector is 1/2 whatever the angle measure is times the radius squared. And that is the area of a slice of pie. So if the angle was pi over 4, sorry, the angle was pi over 2, a right angle, which gave you a quarter of the circle, that would give you 1/2 times pi over 2 times r squared, which would be 1/4 pi r squared, which is 1/4 the area of the circle. So it totally seems valid. Okay, so let's go over here. So for sector OCP, the radius is OC or OP, whichever one you want to write. So I'm going to say that the area of this is 1/2 times the angle theta times the radius of this smaller sector, which I'm just going to call OC squared. The area of the triangle OCB is 1/2 the base, which is OC, times the height, which is CB. The area of the larger sector is 1/2 times the angle times its radius squared, and its radius is OA. Again, if you have questions, you're welcome to ask them. All right. Let's make this a little simpler. Looking at this right triangle for a second, noting that the radius has a length of 1. If I were to find, I really wish I had a little bit more room over here. Right over here, fine. Sine of theta is equal to the opposite over the hypotenuse. The opposite is BC. The hypotenuse is 1. So BC or CB, sorry, it's a little hard to see, I imagine. Zoom in a little bit here. That's equal to sine of theta. In a similar way, cosine of theta is equal to the adjacent, which is OC, over the hypotenuse, which is still 1, which is just OC. So what I want you to see here is that the length of BC is equal to sine of theta. The length of OC is equal to cosine of theta. And sorry, I know my face is in the way here. Sorry. All right, so we're going to rewrite this. We're going to have 1/2 times theta times OC squared is going to be cosine squared. Less than or equal to 1/2 times OC is cosine of theta. CB is sine of theta. Less than or equal to 1/2 times theta times OA is 1, because we said this circle had a radius of 1. All right, I'm on my way. My goal now is to use the squeeze theorem. And to be able to do that, I want to make the middle look like the thing I'm trying to take the limit of. So I'm going to write sine theta over theta instead of sine x over x. So let's multiply everything by 2. We've got theta times cosine squared theta less than or equal to cosine theta, sine theta less than or equal to theta. let's divide everything by by cosine, sorry. So cosine squared divided by cosine, I'll still be left with a cosine. So I'll have theta times cosine theta less than or equal to sine theta less than or equal to theta divided by cosine theta. And finally, let's divide everything by theta. So cosine theta less than or equal to sine theta over theta less than or equal to theta over cosine theta times 1 over theta or divided by theta will give me 1 over cosine theta. Right, we're about to get to the big kind of conclusion here. So any questions about any of the steps I've taken here? I'm happy to clarify. Yeah. So from this step to this step, in fact, let me actually, that's a good question. So from here to here, I multiplied everything by 2, which is totally valid. And then in the next step, I divided everything by cosine of theta. And the next step, I divided everything by theta. I suppose I could have done that all at once, probably, but I wanted to show all my steps. And it's to say, in this first step here, I said that OC was equal to cosine theta and CB was equal to sine theta. So those were all the things I did in each step. From this step to this step, I replaced OC with cosine and CB with sine and OA with 1. From this step to this step, I multiplied everything by 2. So 2 times 1/2 is 1, 2 times 1/2 is 1, 2 times 1/2 is 1. From this step to this step, I divided everything by cosine. Cosine squared divided by cosine gives you a cosine. Cosine divided by cosine is 1. And theta divided by cosine became theta divided by cosine. And finally, the very last thing I did was divide everything by theta. Theta divided by theta give me a 1 times cosine. Sine theta divided by theta is sine theta divided by theta. And theta over cosine theta divided by theta is 1 over cosine theta. Or if you prefer, you could say theta over cosine theta. Instead of dividing by theta, you could say you're multiplying by 1 over theta, and that is equal to 1 over cosine theta. And now we're at the point where the thing that's in the middle of our compound inequality is the thing we want to take the limit of. So of course, we don't do that. We take the limit of the outer parts. So we're going to take the limit as theta goes to 0 of cosine of theta, which is nice. We can just plug it in. We plug it in, we get cosine of 0, which is 1. Similarly, we take the limit of the right-hand part as theta goes to 0 of 1 over cosine. Or you can write secant of theta if you prefer there, although I think 1 over cosine is just fine. And then plugging in, you get 1 over cosine of 0, which is 1 over 1, which is 1. So by the squeeze theorem, you have no choice. The middle part has a limit that is also 1 as theta goes to 0. The limit of sine theta over theta is in fact 1. Kind of cool. Now, do you have to know this geometric argument? Definitely not. Is it nice to have seen it? So maybe you believe it just a little bit more. Yeah, it is. And so what we're really saying here is that, so I'll just point out, right? Look at things geometrically for a second. This length here, BC, that length is sine of theta. And the actual angle theta, so remember, do you guys remember the formula for arc length? Is that probably not? But the formula for arc length, just like the formula for the sector, has to do with the radius. So this arc length here, from B to A, that arc length there is r times theta, which is how we get the circumference formula, right? The circumference of a circle is 2 pi times the radius, or in other words, the angle 2 pi times r. Here we're just using a different angle, theta. But our radius is 1. So look, this length here is really just theta. So what we're saying is, as the angle gets smaller, sine of theta, which is this length here, and theta, which is this length here, their ratio is closer and closer to 1. Or in other words, as the angle gets smaller, those two lengths get closer and closer to being equal to each other, which visually looks reasonable, right? Those two lengths look like they could be pretty close to each other. And if the angle gets smaller, I'm going to take a risk here and try drawing it. Right, if the angle is smaller, this length here and this arc length here are even closer to the same length. That's what this limit is really saying, that those two lengths, as the angle gets smaller, are closer and closer to each other in value. So the limit of the ratio is in fact 1. In practice, what does this mean for us? It means that whenever you see the limit, I'm going to say it very generally. I'm going to use the word I use a lot, stuff. The limit as some stuff goes to 0 of sine of the stuff going to 0 over the same exact stuff, that limit is going to be 1. So for example, it would be true if I said the limit as x goes to 0 of sine of 6x over 6x is in fact equal to 1. Because 6x is going to 0 and I have sine of the thing going to 0 divided by the same thing. Or if I said the limit as x approaches infinity of sine of 1 over x over 1 over x. I have sine of something over the same something. And let me ask all of you, are the somethings, are the 1 over x's going to 0? Indeed they are, right? Because x is going to infinity, 1 over x is getting closer and closer and closer to 0. So this is also equal to 1. Things start getting more challenging when we start asking questions like, what's the limit as x approaches 0 of sine of 3x over 7x? By the way, I should have said, although I didn't, all of these are 0 over 0 types of limits. If you actually plugged in 0, you would have sine of 0 over 0, which is 0 over 0. Or if I plugged in infinity, you have sine of 0 over 0, which is 0. Which is an indeterminate, sorry. Here I have sine of 0 over 0, which is 0 over 0. But now the issue is the stuff's not the same. I don't have sine of 3x over 3x. I have sine of 3x over 7x. There's a number of ways people like to get around this. I have found the easiest way, in my opinion, is to write down what I wish I had. So actually, first I'm going to write down what I have. But I'm going to break it up into 2 fractions. A fraction that I'm going to make look like how I wish it was, and kind of the leftovers. So I have sine of 3x divided by 7x. And now I'm going to ask the question, what do I wish I had beneath sine of 3x? Right. The answer is not supposed to be terrible. But I can't just divide by 3x. I have to account for that by also multiplying by 3x. Then I can do a little bit of work. 3x divided by 7x, the x's divide to 1. So I'm left with the limit as x goes to 0 of sine of 3x over 3x times 3/7. I don't think you need to show any more work here other than saying it's equal to 1 times 3/7. But if you really wanted to, you could apply one of your limit rules. Limit rule that says the limit of a function times a constant, that constant can move out in front of the limit. This is equal to 3/7 times the limit as x goes to 0 of sine of 3x over 3x. And then that's going to be 3/7 times 1, which is just 3/7. But really, I feel like I've written like twice as much as I really needed to here. Let me show you another example. Let's say I want to find the limit as theta approaches 0 of sine of 9 theta over 6 theta. You might already know what the answer is. Let me show you how I do this with the least amount of acceptable work, in my opinion. I would write this as the limit as theta goes to 0 of sine of 9 theta times something over 6 theta. And then I would fill in the blanks. What do I wish I had beneath sine of 9 theta? 9 theta. But then I have to have 1 up there to balance it out. So that I didn't change anything. I really just multiplied by 1. 9 theta over 9 theta. And then I would say that this is equal to 1 times 9 6. And then I would simplify and write that that's 3 halves. And I think that's plenty of work to show for that kind of problem. Then we do other things like, like we say, for example, how about the limit? So you might have noticed in both of these, we got 3 over 7 and 9 over 6, 3 halves. That doesn't quite happen all the time, but it's not a bad thing to be aware of. What about the limit as x goes to 0 of, sure, sine of 6x squared over 3x squared? Well, this one might work out just fine. Yeah, I know what I was thinking of. This one is going to work out to be what we want it to be. Well, let's still write it out. I do think it's always worth writing sine of 6x squared over blank and blank over 3x squared. If you really wanted to, I've noticed over the years I've gotten kind of tired of being like throwing in extra x squareds everywhere. You could write like the x squared down here and the 3 over there, and then say you need a 6 here and a 6 there. But I think this is fine. I need a 6x squared down here. I need a 6x squared up here. My answer is going to be, I do like the step of writing 1 times 2. Right? If you just write 2, I feel like the person grading your work might not see that you really know what you're doing. But if you say, oh yeah, I know the limit of this part is in fact 1, and 6 divided by 3 is just 2, I think showing that additional step really shows the person reading your work that you have an idea of what's going on. Let's look at a slightly different problem that seems like it might be the same, but is actually not. Limit as x approaches 0 of sine squared of 6x divided by 3x squared. Similar vibe, but not quite the same question. So I'm always trying to break this up into sine of something over the same something, where the somethings are going to 0. Just as a quick check, I do have a 0 over 0 type, right? If I plug in 0 for x, I get sine of 0 over 0, which is 0. Sine squared of 6x is, always write the limit first, sine of 6x times sine of 6x times blank over 3x squared. That's how I would do this problem. Right, I've still got all the same pieces. On top, I have sine times sine. On the bottom, I have 3x squared. And now, beneath each sine of 6x, I wish there was a 6x. There's a 6x down there. There needs to be a 6x up here. If there's another 6x down there, there needs to be another 6x up there. The x's do cancel. X times x is x squared divided by x squared. And so I end up getting 1 times 1 times 6 over 3, which is going to be 36 over 3, which is 12. There's a chat in the chat. Could you please explain why you multiplied by 6x squared on both sides? So I wouldn't say I multiplied by 6x squared on both sides. I would say that I multiplied the top and bottom by 6x squared. And the reason I did that was because, and that's really a question, because I said to myself, before I wrote those down, I said, what do I wish I had beneath sine of 6x squared? And I said the answer, oh, I want 6x squared, because we know that the limit of sine of some stuff over the same stuff as that stuff goes where? Where's the stuff have to go to? Has to go to 0. The inside stuff has to be going to 0 for the limit of that to be 1. But if that's the case, sine of stuff over the same stuff as the inside parts are getting closer and closer to 0, the limit of that ends up being 1. And then this just reduces to 6 divided by 3, which is 2. Let me point out, someone asked, what's the limit as x goes to 0 of sine of 3x plus 1 over 3x plus 1? That limit is not 1. I haven't met all the conditions. Yeah, I've got sine of some stuff over the same stuff, but the inside argument of sine is not going to 0. In fact, here, this would be an easy problem. I would just plug in 0 for x. If I do that, I get sine of 0 plus 1 over 0 plus 1, which is sine of 1 over 1, which is just sine of 1. Sine of 1 is not a nice number. I have no idea, actually. I know it's close to like, I don't know, 0.8 something. If you plug it into a calculator using radians, you'll get a number, but we don't need to. This is what the value is. So, be extra clear here. This limit is only equal to 1 if the top and the bottom, I should say, the argument of sine and the denominator are the same thing, and that same thing is getting closer and closer to what value? 0. Anything else? No dice. So just to kind of keep with that, if I said, what's the limit as x approaches 2 of sine of 6 over x minus 3 over 6 over x minus 3, is this limit not equal to 1? Have I met the conditions? Am I taking sine of something divided by the same something? Is the something getting closer and closer to 0? If I plug in 2 for x, right, x is getting close to 2. What's 6 divided by 2? 3 minus 3 is 0. So yeah, this limit meets the conditions. I have sine of a thing over the same thing, and that thing is getting closer and closer and closer to 0. So this limit is in fact 1. Because we have sine of stuff over the same stuff, and the stuff, which happens to equal 6 over x minus 3, is going towards 0 as x is going towards 2. Or if more easily stated, if I plugged in 2 for x, I would have sine of 0 over 0. Oh, that's good stuff. Oh, yeah. Okay. With a couple more and then we'll move on, because there's always more things to talk about. Sure. Yeah, let's do 1 or 2 more. It's also kind of almost inconveniently true, almost, that the limit as x goes to 0 of tangent of x over x is also equal to 1. It's not hard to figure out if we just do a little bit of work. Tangent is what divided by what? Yeah. So I have sine divided by cosine divided by x. I would encourage you to think of that as divided by x over 1. So that when I rewrite this, I can rewrite it as the limit as x goes to 0 of sine of x divided by cosine of x times 1 over x. And then I can group together the pieces that are convenient to me. I can rewrite this as the limit as x goes to 0 of sine of x divided by x times 1 over cosine of x. There is a limit rule that says if the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist, meaning they're not infinity or negative infinity because those aren't limits that actually exist, then it is true that the limit as x approaches a of f of x times g of x is equal to the product of each individual limit. The limit as x approaches a of f of x times the limit as x approaches a of g of x. Or in other words, the limit of the product of f and g is equal to the product of the limits of f and g. So here, the limit of this sine of x over x times this 1 over cosine of x, assuming both limits exist, which we'll see if they do or they don't in a second, is equal to the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine of x. Excuse me. We know this first part has a limit of what? Right. And then the second part, if I plug in 0 for cosine, sorry, for x, cosine of 0 is 1. So I do get 1 over 1 for that part there. And I end up getting 1 times 1, which is 1. Kind of neat. I feel like there's one more I had in mind here. Oh, I know what it was. Yeah. There's one other important limit we should take a look at real quick with this trig stuff, and then we will move on to greener pastures. So yeah, so I want to find the limit as x approaches 0 of 1 minus cosine of x over x. I feel like, did we do this one to start with? Maybe not. No, we did 1 minus cosine x over sine of x, which is slightly different. But I'm going to approach this one in the same sort of way I approached that very first one, which is by multiplying by the conjugate. Because just, right, 1 minus cosine times 1 plus cosine is 1 minus cosine squared. 1 minus sine times 1 plus sine is 1 minus sine squared. And both of those turn into trig identities. 1 minus sine squared is equal to cosine squared. 1 minus cosine squared is equal to sine squared. So that's an important identity that comes up a lot. Now, I want to be extra careful here. 1 minus cosine on its own is not an identity. We cannot replace it with sine of x as much as we might want to. We have to do the work of multiplying it by 1 plus cosine over 1 plus cosine. As is typical, the things that are conjugates get multiplied out. The things that are not, do not. This is going to become the limit as x approaches 0 of 1 minus cosine squared of x in the numerator, x times 1 plus cosine x in the denominator. We're going to replace 1 minus cosine squared with sine squared. That's sine squared x in the numerator, x times 1 plus cosine x in the denominator. And now we're going to use a pretty typical tactic that we just used in the previous one. We're going to break this fraction up into multiple fractions, one with pieces that kind of look like something we know, and the other one with the rest of the pieces. So in the numerator, I see sine times sine. In the denominator, I see x times 1 plus cosine. I would like to break this up as sine of x over x times sine of x over 1 plus cosine of x. It's still the same thing. In the numerator, I still have sine times sine, which is sine squared. In the denominator, I still have x times 1 plus cosine, which is the same thing I had right there. But now, look what happens. The limit as x goes to 0 of sine of x over x is 1. the limit as x goes to 0 of sine of x over 1 plus cosine x, I can plug in x going to 0 and get sine of 0 over 1 plus cosine of 0, which ends up being 1 times sine of 0 is 0, cosine of 0 is 1, 0 divided by 2 is 0. So this limit is 0. The reason I bring it up is because it does come up a lot, but specifically it comes up when we talk about the derivative of the sine and cosine function using the limit definition of the derivative, which will be coming up in sooner than we probably need it to be. But that's how we use this trig identity to prove that limit, that derivative is what it is. All right, let's see, where am I at here? Sorry. Oh yeah. Sure. Type of limits of trig, we type of squeeze. Yeah, I guess we should probably start talking about continuity. All right. Yeah, well, we have 20 minutes. Sure. Continuity. So hopefully you all remember how I've talked a lot about how the limit of a function doesn't care what's actually happening at the place you're approaching. However, continuity does care. So, for example, looking back at the function I was talking about a little bit ago, I was looking at the limit. I'll write down the function first. I was talking about the function f of x equal to x squared plus x minus 6 over x minus 2. Oh, sorry, there's something in the chat. Let me look at the chat room. If you guys see that I'm ignoring the chat, let me know. These are trig entities, right? So I'm guessing it's a good start. Yeah, it's good to learn the trig entities. So I would specifically say the trig identity, the what I refer to as everyone's favorite trig identity, even though it might not be your favorite, but it's the one that everyone knows the best, is typically sine squared of theta plus cosine squared of theta equal to 1. Or if you prefer x, that's also fine. Whatever variable you want. And then you could rewrite this in two different ways. You could write it as cosine squared equal to 1 minus sine squared. Or you can write it as sine squared theta equal to 1 minus cosine squared theta. There are certainly many other trig identities. This is just the one we happen to be using right now. And then that limit is not a trig identity really, it's just a limit we use often. Yeah. So this function here is equal to x minus 2 times x plus 3 over x minus 2. And I will point out that certainly the limit as x approaches 2 of this function is equal to the limit as x approaches 2 of x minus 2 times x plus 3 over x minus 2. And then you can cancel the x minus 2. So you get the limit as x approaches 2 of x plus 3, which is 2 plus 3, which is 5. And the limit exists as x approaches 2, or really anything, but I'm focusing on 2 specifically. I could also say the limit as x approaches -1 of f of x is equal to the limit as x approaches -1 of x minus 2 times x plus 3 over x minus 2. And then you don't even really need to cancel the x minus 2's. You certainly can, but you also just plug in -1. You get -1 minus 2 times -1 plus 3 over -1 minus 2, which ends up equaling 2. Or if you prefer, -3 times 2 over -3, which is 2. But the point is, the limit exists everywhere, actually. You can pick any value for this function, the limit would exist as x approaches that value. However, this function is not continuous at 2. Because even though the function has a limit that exists at 2, f of x is not continuous at 2. In fact, f of 2 doesn't even exist. if I try to plug into this function actually, and not just take a limit, but actually sub into the original function, can't be done. I get 0 over 0, which is undefined, indeterminate. So the limit exists, limit is 2, the function does not exist at 2. Graphically, I know I graphed it before, I'm going to graph it again. It looks like this. We've got a hole at the point 2, 5. Definitely not continuous. Now, when I say this function isn't continuous, what I really mean is it's continuous almost everywhere, but it's not continuous everywhere. There is at least one point, sometimes more, where it is discontinuous. And that point in this function happens to be when x equals 2. So we could say a lot of things here. We could say this function is continuous on the interval from negative infinity to 2, union 2 to infinity. But it certainly is not continuous at x equals 2. And if I was talking about this function, and I had this, if you asked me, is this function continuous or discontinuous? And I can only say one of those two words, I would say it's discontinuous because it's not continuous everywhere, even though it's almost continuous everywhere. Is that even though it's continuous almost everywhere? Almost was in the wrong place there. So let's talk more about continuity. We'll look at some more examples of functions that may or may not be continuous. And kind of the intuitive way of thinking about continuity is, can you draw the function without lifting your pencil off the paper? So watch me draw this and then answer the question for yourself. So here's my piecewise function, f of x equal to x squared when x is less than 2, and x plus 2 when x is greater than 2. So here I go. So let's see. Here's 1, 2. Here's 1, 2, 3, 4. So it's equal to x squared when x is less than 2. So it's going to be this nice parabola when x is less than 2. Right there like that. And then at the point 2, 4. Oh, it's not actually defined when x is 2. They don't get a point there. And then when x is bigger than 2, it's equal to that line, y equals x plus 2. Continuous? Definitely not. I mean, you can maybe like make an argument that, yeah, I could draw this circle and like go around like that and then like not with my pencil off the paper, but I'm missing the point. Just like the previous function, f of x here is not continuous at x equals 2. And the reason, and I do like to say the reason why a function isn't continuous is because this function is not defined at 2. Because f of 2 does not exist. All right, let's look at a different example. Sorry, let's keep that example on the page though. Let's say I want to look at the function g of x equal to almost the same thing, x squared when x is less than 2. And now x plus 1 when x is bigger than or equal to 2. Well, right off the bat, I have a better chance of being continuous because at least this function is defined when x is equal to 2. The previous one was not. I had no prayer of being continuous at 2. So here, when I graph it, let me be a little bit more careful about what's going to happen here. So when x is less than 2, I still have the same portion of the parabola, y equals x squared. It's going to look something like this. Until the point 2, 4. And then after that point, I'm going to jump down to, well, when x is 2, 2 plus 1 is 3. And I'm going to go off like that. Does that look continuous? No, right? It looks like I jumped off the paper to move down to the next point and then continue on. I definitely could not graph this without lifting my pen off the paper. Now, how do we see it's continuous, not continuous from a mathematical perspective? Well, first I'll point out that f of 2, sorry, g of 2 does in fact exist. g of 2 is equal to 2 plus 1, which is 3. Let's look at the limits. If I look at the limits as we approach 2, well, there's a different function on the left than there is on the right. Then you look at the limit as x approaches 2 from the left-hand side. Now, I could actually write things, or I could just look at the picture. If I look at the picture, as x approaches 2 from the left side, the y values are getting closer and closer to positive 4. I could also use the piece of the function and say, oh, that's the limit as x approaches 2 from the left of x squared, which is just 2 squared, which is just 4. Note, I'm not plugging in 1 or 1.5 or 1.9 or 1.999. I'm actually plugging in 2 and getting 4. Reminder, the function doesn't equal 4 when x is 2. What this says is as x is getting close to 2 on the left-hand side, the function is getting really close to 4. We're not saying the function equals 4. We're saying it's getting close to 4. It might actually also equal 4, but that's not what we're saying. On the right-hand side, the limit as x approaches 2 from the right of g of x. Well, that's when we're going to use the piece of g of x that's bigger than 2. So that's going to be, I should say, the piece of g of x when x is bigger than 2. Sorry, I misspoke there. X approaches 2 from the right of x plus 1. Plugging in, not 2.3, not 2.1, not 2.001, actually plugging in 2, we get 3. So what we're saying there is that as x approaches 2 from the right, the function gets closer and closer and closer to 3. It also happens to be true that if you plugged into this function, you would actually get 3, as we did in the beginning, right? G of 2 was in fact equal to 3. The limit, on the other hand, from the left is 4, from the right is 3. The overall two-sided limit doesn't exist because those values aren't matching up. So the limit as x approaches 2 of g of x does not exist. So one way a function might be discontinuous is if the function doesn't exist at the point you're interested in. Another way a function might be discontinuous is that even if the function exists there, the limit might not exist. And a third way a function can be discontinuous is, say your function is x squared when x is less than 2. Sure. 3 when x is equal to 2, and x plus 2 when x is greater than 2. Now we're essentially back in the first function situation here, but now we're defining the function to be equal to 3 when x is equal to 2. Still not going to be continuous though. Let's draw it. Try to draw it well. Yeah, it's gonna look like this. That's okay. Finally. There's my function drawing. And we can see that f of 2 certainly exists. It's equal to 3. The limit certainly exists. The limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left of x squared, which is 2 squared, which is 4. And the limit as x approaches 2 from the right of f of x is the limit as x approaches 2 from the right of x plus 2, which is 2 plus 2, which is also 4. So the overall limit as x approaches 2 of f of x is equal to 4. But the limit and the function don't have the same value. So this function is discontinuous at 2 at x equals 2 because the limit as x approaches 2 of f of x does not equal f at 2. And that's actually really the definition of continuity is that for a function, and I'll write this down in a second, that for a function to be continuous at a point, the limit value at that point and the function value at that point have to be the same. Notably, they both had to exist first before they could be equal to each other. So what we usually say is that you have to meet three conditions, which all are really summed up in the last condition. So here's how we're going to write this. We're going to say that f of x is continuous at a if the following three things are true. One, f of a exists. Two, the limit as x approaches a of f of x exists, which usually means the limit from the right and the limit from the left have to equal each other. So typically we need to check the limit as x approaches a from the left is equal to the limit as x approaches a from the right. And finally, if both of those conditions are met, then those two things also have to be equal to each other. The limit as x approaches a of f of x has to equal f of a. And the reason I'm boxing that is because really all you have to say is that. If your function meets this criteria, it had to have already met things 1 and 2. It's just usually easier to first check that 1 is true. And if it's not, say it's discontinuous. And then check if 2 is true. And if it's not, it's discontinuous. And then finally, if 1 and 2 are both true, then check to see if they're the same. If they're not, it's discontinuous. So if any one of these three things fails, your function is discontinuous at the point of interest. If all three of them don't fail, then your function is continuous there. So, what time have we got? We got like 5 minutes. Let's look at something like f of x equal to x squared when x is less than 3. Sure, 9 when x is equal to 3, and 4x minus 3 when x is greater than 3. And someone might ask this question in the most annoying way possible, which is, where is this function continuous? Which I always find to be a little annoying, but it's often how it's phrased. So where is f of x continuous? Which is really the question, tell me where it isn't. And then, or find where it isn't, and then tell me the rest. So this function is certainly continuous when x is less than 3, because it's equal to x squared, and any polynomial is continuous on its domain. So that parabola that's opening upwards from negative infinity up to positive 3, certainly going to be continuous on that domain. Likewise, the straight line, also a polynomial, 4x minus 3, is continuous when x is greater than 3. The only point of contention is when we switch from being less than 3 to being bigger than 3. So we have to look and see, is this function actually continuous when x is equal to 3? Because everything else is a given that it's going to be yes. So the question here is really, what's happening at x equal to 3? So we're going to check the 3 things. So thing 1, what is f of 3? Well, looking at my piecewise function here, I have to pick the piece where x is equal to 3. So f of 3 is going to be 9. They're not making me work for it at all. They're just telling me it's 9. Part 2, we have to see if the limit exists. Now, some of the time you'll have a function that's defined to be the same on either side of your point, but a lot of these piecewise ones are going to be something different on the left and the right of whatever value we're looking at. So I'm going to look at the limit as x approaches 3 from the left of f of x, which is the limit as x approaches 3 from the left of which piece am I using? Am I using x squared? Am I using 9? Or am I using 4x minus 3? Right, because I'm left of 3, and that's when x is less than 3. And then I can just plug it in and get 3 squared, which is 9. Good news so far. Also, by the way, I'll point out, if that limit had been 10, I could kind of stop there. I could say, well, I know either the limit's going to not exist, which means it's not continuous, or the limit is going to exist and it's going to be 10, which means the function won't be continuous because the limit value and the function value won't be the same. It's usually just easier to find the other half of the limit and then say how it isn't continuous, either by the limit not existing or by the function limit not being the same. But if we look at the limit as x approaches 3 from the right-hand side, that's going to be the limit as x approaches 3 from the right-hand side of 4x minus 3. We plug in, we're going to get 4 times 3 minus 3, which is 12 minus 3, which is 9. Great. The limit is 9, which is not enough. We also have to say that the function is 9. So 3, I like to say f of x is continuous at x equals 3 because both the limit as x approaches 3 of f of x, which is equal to 9, and f of 3 itself are equal to the same thing. And then furthermore, I should then go back and answer the original question, which is, where is this function continuous? This function is continuous everywhere. Because we already knew it was continuous everywhere except for 3, and now we have also seen that it's continuous at x equal to 3, so it's continuous for every real number. If you were to graph it, it would look something like this. That's not my favorite. So there's the point 3 comma 9, but then it continues to be, right, we get that point filled in, and then it's equal to 4x minus 3, which, goes off somewhere like that. So yeah, totally continuous. There's no jumps, there's no points missing, good to go. And it is time for me to stop talking.